momentum, impulse. Real quick video here. For one, this is just one pretty focused topic. It all really starts with Newton's second law and this idea of impulse. I just want to show you which section of the review book we're in here. Ooh, almost energy. There we go. We're over on like page 56, 57, 58. So very good notes in the review book there. So let's first talk about what's going on here, how we define impulse momentum. All right, so it really all starts off with force equals mass times acceleration. So, and one of the reasons we do this at all is to investigate that force of contact when two things collide, right? Force of contact is the force that's going to cause one of these objects to accelerate. So when they hit, they apply a force on each other, equal and opposite. We'll call that cart 1, cart 2. So F of 2 on 1, force of 1 on 2 pushes that way. They're the same magnitude, right? But actually this one's negative. So if it's a 100 Newton force on this one, it's negative 100 Newtons. If it's a 100 Newton force on this one, it's positive 100 Newtons, all right? So it's a contact force. So if I just look at one of them, all right, I'm going to zoom into just one of the carts. All right, let's say the one on the left that was moving to the right to start off with. So that contact force, all right, causes an acceleration. Well, what's an acceleration? Well, an acceleration is a change in velocity over time, right? So that force causes this velocity to change. So if it was immediately moving this way and initially moving that way and the force is to the left, then this object's going to slow down, right? It's going to have a change in velocity. So let's write Newton's second law now as F equals m delta v over t. All right. So the amount the velocity changes by depends on its mass and the amount of time that force acts for. So the next thing we do is multiply both sides by time. And we end up with this. Force times time equals mass times change in velocity. And that's kind of cool, right? So the force, the amount of time it acts for, the product of those two, ends up being equal to the mass of the cart times whatever its change in velocity is. So this is kind of like, this side of the equation is kind of like the properties of the cart, its mass and velocity. This is the force and the amount of time it's acting for. All right, so it's like the cart and the force, the cart and the force. The application and what changes or what doesn't change being the mass. So this side of the equation we end up calling impulse. This we call change in momentum, which means that the momentum at some, which is, well, delta p, right? P at some point in time is simply just the mass times the velocity at that time, right in the glare. Sorry about that. Delta p, right? So, which would be P final minus P initial. Final momentum minus initial momentum. So the momentum at some individual time is simply the mass times the velocity of the cart at that time. Impulse, we give a symbol to, which unfortunately is J, delta P for change in momentum, lowercase p. J, it's not a wonderful variable because it's the same variable that we use to represent the unit of joules, right? So that's always kind of annoying. The unit for momentum or impulse is typically, impulse we say is Newton times meters, and change in momentum is kilograms times meter per second, but in fact those are the same thing. If you put newtons in terms of its base units, kilograms times meters per second squared, multiply that by meters, you end up with the same unit over here. Okay, so anyhow, this is the basic of the equation. So how do we use this? Well, we say, okay, determine the change in momentum, determine delta P for a cart that has a negative 10 Newton force acting on it for 5.0 seconds, right? Terrible handwriting, sorry about that. So note that I put the negative sign on here because the sign matters. Impulse, momentum, change in momentum, they're all vector quantities, okay? So determine the change in momentum for a cart that has a negative 10 Newton force acting on it. So for 10 seconds. So delta P equals J, which equals force times time. J is impulse. So the change in momentum ends up being equal to impulse, which is equal to force times time. So the change in momentum of the cart is negative 10 newtons times 5.0 seconds. I said Newton meters on that previous screen. That's a mistake. Oh, it's Newton seconds. I was thinking that didn't cancel out, right? That was dumb. Sorry about that. The unit are Newton seconds, or you know why I said that? Because a joule is a Newton meter, and J is, that's nonsense. Sorry about that. Newton seconds or kilogram times meter per second. I'll put something in the comment of this video on YouTube to try to avoid you people from like stopping before they get to this part and trying to figure out what I did. So we get negative 50 Newton seconds is the change of momentum. So that means if the car is moving to the right, it has a positive momentum, it's going to slow down, lose that momentum as this force acts. Now, the other important thing here are collisions, conservation of momentum. All right, so when two things collide, I'm going to draw them kind of tall here so we can really focus in on that contact force. Force on one, force on two. When two things collide, pretend like this is like where the collision is occurring, right? They're pushing off. All right. Obviously, they're going to be in contact for the same amount of time, right? Each cart. I'm going to call this force of, we'll call this cart 1, cart 2. Force of 2, 1. Force of 1, 2. That's the same force, opposite magnitude, right? My dog's barking. He's out back. He wants somebody to come out and play. I have the garage door open, so that's why you could hear him. So each of these forces act on each of these carts the same amount of time, right? And it's the same force. So when we look at this one here, delta P of cart 1 is equal in magnitude to the delta P of cart 2 because they each have the same magnitude of force acting for the same amount of time. But you should note that those forces, if F12 is positive, then F21 must be negative because their contact force equal in opposite direction. All right, F12 equal in opposite direction, so the change in momentums are equal and opposite. So let's put a number on these. Let's let time be equal a ridiculous amount of time, 1.0 seconds. Very few collisions take 1 second, unless it's like something in an airbag or something like that. And let's make this just the positive 10 and negative 10 Newton. So this one's change in momentum would have to be negative 10, because F21, negative 10 Newton times seconds. This one's would have to be, they have to be the same magnitude, would have to be positive 10 Newton seconds. So the magnitude of the change in momentum is the same, however, they're opposite signs, opposite directions that change momentum. So whatever momentum one gains, the other one loses. And this is true in any collision. Anytime two objects collide, whatever the change in momentum is of one, it has to be the same change in momentum of the other object. However, it can be opposite signs, opposite directions, totally different velocities too. If they're different masses, then to have the same change of momentum, they must have different velocities when they bounce off of each other or whatever. All right, so what this tells us is, so if one's gain in momentum is equal to the one's loss in momentum, or, you know, vice versa, whatever you want to say, then if we treat this as a system, right, since this has become some system, a system being two objects and their environment collected in some defined boundary, so to speak. If this is a system, delta P of the system must be equal to 0, because one has positive, so this one gains positive 10 Newton seconds, this one loses 10 Newton seconds, or gains negative, we might say, you know, gains negative 10 Newton seconds of momentum, this one gains positive 10 Newton second momentum. The total gain in momentum of the system is 0. The only time a system can gain momentum is if a force comes from outside the system and acts on it, or if some sort of energy is released inside the system. If some sort of energy is released inside the system, then we can get a change in momentum. If a force just, you know, gets triggered or something inside the system, like a spring between the two cars. So this brings us to the fact that if the system, momentum of a system can't change during a collision, that means the total momentum, total P before, this is bad. I'll write the reference table. P before must equal P after. The momentum before the collision must equal the momentum after the collision. Right? So we saw lots of examples about that in class, and we're starting to get to the point where you can kind of, you know, if you want to look at some of these examples, go back and look at some of the solutions for the previous worksheets we did, right?